This video is about voltaic cells, which is a way that we can make spontaneous redox reactions arranged in such a way that electrons flow and thereby we can make them do work. Redox reactions involve electron transfer. Here's an example of a redox reaction. Let's split this up into an ionic equation and then make it into a net ionic equation. Zinc we can't split up. Aqueous copper 2 sulfate, we can make copper 2 and SO4 2 minus. Same thing with zinc sulfate. And copper is just a metal. Sulfate's a spectator here. So this boils down to zinc and copper 2 plus becomes zinc 2 plus and metallic copper. Now, how are electrons transferred here? If we imagine this reaction occurring, on the left-hand side, this is before the reaction. On the right-hand side is after the reaction has occurred. If we could zoom in on a little piece of the zinc, all the way down to the particle level where we could see atoms, this is a little piece of our strip of zinc. Each one of these silver spheres represents a zinc atom. Out in the solution are sulfates, which remember are spectators. They're not really doing anything here, but there are copper ions. And those copper ions are going to get reduced. How does that occur? Electrons leave the zinc particles and get transferred out to the copper ions. That makes the zinc a 2 plus ion and no longer really part of the metal. The copper becomes an atom of copper. It's no longer an ion. That zinc ion goes out into the solution and that copper atom sticks to this strip of zinc. And this just happens over and over and over again until the zinc strip is coated with metallic copper. How voltaic cells are different is they separate the oxidation that's occurring here and the reduction into two different spaces. Voltaic cells are different because they're going to separate the oxidation and the reduction into two separate spaces. The oxidation is the gaining of electrons. So thinking about half reactions, zinc is becoming zinc 2 plus, and that's a loss of 2 electrons. And the copper 2 plus is gaining 2 electrons to become copper. And if we make these happen in two separate spaces, those electrons can be forced to move from one of these beakers to the other. Each beaker is called a half cell. So on the right-hand side, zinc is oxidizing to make zinc 2 plus. The electrons that it releases are needed for the reduction that's going to occur on the left-hand side. So they move down the wire, enter the solution through the copper strip, and reduce copper to copper atoms, which then increase the mass of the copper strip. Now, as this occurs over a little bit more time, we start to get a buildup of positive charge on this side because we're producing zinc ions from neutral zinc, and we're not making any more sulfates. So the negatives in this solution are starting to get outweighed by the positives. The opposite thing is happening on the left-hand side. We still have just as much negative charge from the sulfate ions that are in solution, but we're slowly taking away positive charge from the coppers that are being reduced. So this starts to develop an overall negative charge. Charge imbalance is something that is going to prohibit this reaction from going on. Nature kind of hates that. So here's how we can make the circuit complete and balance the charge. We could put a tube here that connects the two sides and has a kind of leaky ends on both sides. If this tube has an ionic compound in aqueous solution, for example, sodium sulfate, sodium ions can leak out this side and add positive charge to this side of the reaction and balance that increasingly negative charge. And the sulfate ions can leak out this side and bring some negative charge in to the right-hand side beaker to bring the right-hand side into balance. And this completes an electrical circuit. We have negative charge flowing this way in the form of electrons and then this way in the form of ions. So it's a complete circuit. And with that device in here, that tube, which is called a salt bridge, the reaction can continue. The driving force that pushes the electrons from one side to the other is called potential. So cell potential is the energy that's carried by the flowing electrons, and it's also the driving force that's pushing those flowing electrons. We can measure this with a device called a voltmeter. For this particular reaction, we can see the voltmeter giving a reading of 0.81 volts. Volts are an electrical measure. We'll have some more details about what that unit means later on. But the bigger that is, the bigger the potential is to push electrons from one side of the reaction to the other. This thing is called a voltaic cell, and it's the simplest kind of battery to understand. Let's identify the parts of the voltaic cell. On the right-hand side here, we have what's called the oxidation half cell. It's called that because that's where the oxidation is occurring. Zinc is oxidizing to zinc 2+. The zinc strip is the anode. The anode is where oxidation occurs. The left-hand side is a reduction half cell. The reduction half cell is where reduction occurs. Copper ions in this solution are being reduced to copper. And the electrode in the reduction half cell is called the cathode. How to keep these straight is anode and oxidation both start with vowels, and cathode and reduction both start with consonants. So if that helps you memorize, then that's good. And then I've already referred to the little tube with an ionic compound that's in aqueous solution in the middle. That's called the salt bridge. Instead of drawing pictures all the time, sometimes people use what's called line notation as a kind of shorthand for describing these voltaic cells. Here's how it works. This double bar is the salt bridge, and that separates the anode half cell from the cathode half cell. So it's anode, bridge, cathode. That's the format, A, B, C, anode, bridge, cathode. That's a convenient way to remember that. Now on the anode side, we're separating this into the anode itself, and then the anode solution, then the salt bridge, and then we're doing the same thing on the cathode side. The cathode solution is listed closer to the salt bridge, and then the cathode itself is on the outside. Let's do some practice. Here's a voltaic cell that's drawn in this picture. Let's write the anode and cathode half reactions. It tells us that the direction of electron flow is left to right. So that means electrons are going out of the iron half cell and into the silver half cell. So that means reduction is occurring at silver side. So silver ions are gaining an electron and becoming silver. And then on the left-hand side, we see we have iron 2 nitrate as our solution. So we can assume that iron is oxidizing to iron 2 and giving up 2 electrons. What's the overall cell reaction? Well, the number of electrons gained and lost has to be the same. So Fe becomes Fe2+ to give 2 electrons. So we'll have to take this Ag+, which is gaining its 1 electron, to become Ag, and we'll have to double that. So the overall reaction is, when we sum these two together, Fe plus 2Ag+ makes Fe2+ and 2Ag. What's the line notation? Let's make some space for that. Remember, it's anode, bridge, cathode. So where oxidation is occurring is in the iron side. So the cathode is Fe, solid. The cathode solution is Fe2+ aqueous, or FeNO3 aqueous. Then the bridge. Then next comes the cathode solution. That's Ag+ aqueous, or AgNO3 aqueous. And then a vertical line, and then the cathode, which is silver solid. If the salt bridge contains Ki, what role does each ion play? Well, remember, this is going to become increasingly positive because that's where oxidation is occurring. We're getting more and more irons with no additional nitrates to balance them. So iodide ions are going to go in here because they're negatively charged to balance that increasingly positive charge. And then this is going to become increasingly negative because we're reducing silver ions, so that positiveness is not in the solution, but there's still as much negative charge from the nitrate as there ever was. So this is becoming increasingly positive. So the potassium ions, which are positive, will leak out this side of the salt bridge to balance that negative charge and bring a little more positiveness to it. Here's another one. Here we have the line notation. From this, we're supposed to write the anode and cathode half reactions. So remember, it's anode, bridge, cathode. So the oxidation is copper to copper 2+, and that's giving up 2 electrons. Why do I know it's 2+? Because because this is copper 2 sulfate. And the cathode, well, the gold is what's reducing. It's gold 3 here. That would require 3 electrons, and it's making gold. Overall cell reaction, 3 electrons are gained by the gold reduction, and 2 are lost by the copper. So I'm going to have to triple the copper half reaction and double the gold half reaction. So it's 3 copper plus 2 gold 3 plus, makes 3 copper 2 plus and 2 gold. Sketch the voltaic cell. Well, on one side, I'm going to have a copper strip, and inside this solution, I'm going to have CuSO4 aqueous. On the other half cell, I'm going to have a gold strip, and then I'm going to have AuNO3 aqueous solution. And of course there'll be a wire connecting these two, and then I have to have a salt bridge. These are solutions, of course, and that salt bridge has to dip into both of those solutions. So there's the sketch. What's the direction of overall electron flow? Well, the oxidation is occurring over here on this side. So that produces electrons. The reduction is happening over here, and that requires electrons. So the direction of electron flow is from the oxidation to the reduction.